Hello students, so today's topic of discussion is diffusivity in nanomaterials. Now the word diffusivity is actually the quantitative representation of the phenomena of diffusion. Diffusion is the process where there is a flow of an entity from a higher concentration to a lower concentration. That means when there is a concentration gradient. Now this concentration gradient can be of gas, can be of number of ions, a number of molecules, number of atoms. Now the the law which actually governs this diffusion, the process of diffusion, is called Fick's law. Rather, it's fixed first law, which says that the flow or the diffusional current or the diffusion current density or the flow of the entity per unit area or volume is equal to minus d delta C. So this is the concentration gradient as we have discussed previously. This is the diffusion current, and this quantity, this one d, is actually the diffusivity that you will be discussing. Now the negative sign of course is due to the fact that a diffusion flows from higher concentration to a lower concentration. Now why this is called a fixed first law? Because there is also a fixed second law according to which the current density is, or the diffusion current density is equal to, let's say I will call this one as d, okay, let's call it as d dash into del square c. That means this is a second order relation. This is the first order equation, this is second order equation. So here we are assuming that the change in the concentration as the current flows is constant. However, in this case it represents the fact that the change in concentration varies. So put it in a clear way. It's Fick's first law and this is Fick's second law. This operator is the Laplacian operator. And it means del square by del x square plus del square by del y square plus del square by del z square. Now, in a nanocrystalline material, as we have seen in our previous classes, in a nanocrystalline material, we have grains or crystallites, or whatever way we may put it, having a particular atomic orientation for each particular grain, and we have grain boundaries, or the areas which divide one grain from another. the diffusion occurring inside the grain, like in this case, the diffusion occurring inside the grain is through lattice, the atomic lattice. So we will call it as a TL. However, the diffusion occurring along the grain boundaries, we will call it as DGB. And since there are a lot of defects in the grain structure, including the grain boundaries, like dislocation, half plane of atoms, dislocation, and the surface itself. These are all considered to be defects. There are triple junctions and quadruple junction. So the diffusivity through the different defects, or there can be diffusional paths through the defects. Now these paths are much easier paths for the atoms to travel as compared to the lattice. This is mainly due to the fact that when there is a movement of atom from one region to another due to a concentration gradient, this movement requires breaking and forming of bonds. Now, in a lattice, uh, in a lattice, there is particular bond energy associated with each bond. However, so this bond energy has to be overcome for the atoms to travel, and this is actually also called the activation energy Q. So inside the lattice, we can say that the diffusion coefficient T can be related to the activation energy by this equation. Exponential minus Q by RT. So it shows that the diffusion depends upon not only upon the activation energy, that is actually related to the bond strength, but also to the temperature. The higher the temperature, the more energy these atoms will get for making, breaking and making bonds, and the traveling becomes much easier. Now, comparing the lattice diffusion and diffusion through the lattice and through the defects, as previously told, it has been found that the activation energy of the lattice for required for a diffusion is obviously greater than the activation energy required for diffusion through dislocations, and which is greater than that through the grain boundaries, and lastly the surface. So L stands for the lattice, D font stands for the dislocation course, GB stands for the grain boundary, and S for the lattice. And taking a practical example, it has been found that in case of nanocrystalline copper, the diffusion through the defects, that means if you combine all the different paths of diffusion which are considered to be defects, each about 12 to 14 or say 14 to 20 times more than the diffusion through the lattice of the copper. So one can imagine how easy the diffusion path is. And the defects, and now the reason why this is because this bond energy issue, or the bond energy, is much lower in the case of defects. Or the activation energy, or the energy required, since the atoms are not arranged in a particular pattern, and they are much open structures. The defects have got much open structures, so that's why this is the case. Now, if you plot the different diffusional diffusivities, so log of diffusivity d, which comes as meter square per second. So why? Because the flow of atoms diffusion is through a particular area and for a particular time. So it is the amount of area covered per unit time. So that is why this meter squared per second unit. You take log d and divide it by a temperature called normalized temperature. That means melting point by the temperature supplied. This is the normalized temperature. Then what we can find is this is the slope if the diffusion is through the lattice, whereas the grain boundaries is this one, and for the surface is this one. Now it implies the fact that since the activation energy of grain boundary is much less than the activation energy for the lattice, slopes are much smaller in the case of DGP. See, the slopes is small. Actually, it should be a little like this. The slopes are much smaller. Now, secondly, at low temperatures, so the difference is higher. The diffusion through the grain boundaries is much higher. So, as we reduce the temperature, the diffusivity in the case of grain boundary has been found to increase, or rather, the defects becomes more active at lower temperatures. However, as the temperature increase, the diffusion of the grain boundary it matches with the lattice diffusion. And now, in the case of conventional materials, that means those are not nanomaterials, the volume fraction of the grain boundary is much lower. So the effective diffusion, that is considering all the different diffusional paths, it is mainly represented by the diffusion through the lattice. Now, this effective diffusion again has got a mathematical representation. If we consider the diffusion through the defects as well, so this is equal to, of course, this lattice diffusion, primary diffusion, plus the grain boundary thickness by the grain size, the ratio of that, into the diffusivity of the grain boundary, plus the volume fraction of the dislocations with respect to the grain size into grain boundary diffusion through the dislocation, and similarly the volume fraction of the surface divided by the grain size into grain boundary diffusion through the surface. Okay. So since these values, these coefficients, they keep on increasing as we decreasing d. So it indicates that as we are decreasing d, the d effective diffusion, it shifts from dl to effective diffusion through the defects. It's not only dl, the value importance of dl goes down. Okay. Now let us move on to little a different aspect, which is actually related to the diffusion, but which also involves the effect of temperature. Now, as in normal cold screen materials or normal materials, we know that the nucleation and the growth process involves formation of small crystallites. Now, this is a melt, for example, any melt or a metal in liquid state. Now, as we increase the temperature, there is formation of small crystallites of any particular phase, and they start to form. So there is a nucleation and growth process taking place, and there is an involvement of Gibbs free energy, and there is an effective Gibbs free energy. Corresponding to that, we have an effective radius. So if the radius of the crystallite is more than r star, then the grains grow. Otherwise, the small crystallites dissolve into the solid, and this actually ultimately leads to what we get as the grain structure. Now, in this grain structure, if we keep on increasing the temperature, the grains start to grow. The grains keep on growing, and this is representative of the fact that taking an XRD pattern where we have intensity and 2 theta. Suppose we have a peak like this for a temperature T. Now if we increase the temperature T dash greater than T, then the peak's intensity of the peak increases, which indicates that more crystallization has taken place. Now, in the case of nanomaterials, the the factor that comes into the picture is the surface to volume ratio. If we assume the grains to be a spherical shape, that's why we present them as D, considering it is the diameter of the grains. So surface to volume ratio, normally if you take any material, and especially for the case of the sphere, so surface is 4 pi r square and volume is 4/3 pi r cube. So it's effectively proportional to 1 by r. So a decrease in the radius or the diameter will cause an increase in surface to volume ratio. Now then the smaller the crystallite, the more will be the surface to volume ratio. Now the grain boundaries are high energy states, and since they have a mode S by V ratio. Now a system, normally any system, it has the tendency to reduce its energy and come to the lower energy state. So this is actually the driving force for reduction of grain boundary. So the driving force is to reduce the volume fraction of the grain boundaries, and this is what leads to the grain growth. So as we increase D, automatically my S by V ratio will go down, and so I reach a state which is of lower energy state. This is called coarsening of grains, or increase in size of the grains, and involving grain boundary migrations. Based upon grain boundary migration. Now this grain boundary migration is predominantly a diffusion controlled process. And it is dependent upon the firstly the composition, which is usually fixed unless and until we are doing some sort of alloying or other things. We will consider it as the composition to be fixed. Consider this one to be fixed. But it depends upon another important aspect, that is temperature. So as we had the Arrhenius equation relating diffusivity with temperature, so similar to that we also have an equation related to the grain growth. So equation stands that R to the power n is equal to R O to the power n into exponential minus Q GB by RT. Okay. So this is a material constant, and this is the radius of the grain or the crystal that is being growing, and this n is an exponential factor which is usually taken 2 for a microcrystalline or a normal material, normal conventional material. Now, if we switch our the same discussion in the case of nanomaterials, of course, in nanomaterials, the activation energy for the grain boundaries will go down simply because of the fact that the volume fraction of the grain boundaries, they go up. So so this actually leads to a higher driving force for grain growth. So n is more than 2 in the case of nanomaterials. And also, this is the fact which implies that the nanocrystalline solids are much less stable. They cannot be made stable at the normalized temperature, that is T by Tm. So it also indicates the fact that the nanomaterials are also not suitable for high temperature applications, because the questioning will start soon. Now, to solve this problem, what is required is that we need to somehow stop the grain growth process. So if these are the different grains, and with increase in temperature, the grains are increasing in size, we need to stop it. And there are different means by which we can stop it. One of them is called Zener peening. Zener peening is nothing but suppose this is grain, and a temperature is causing these grains to grow. So if temperature is increased, say, the grains grow in size. So there is a grain boundary migration that is taking place. Now in this case, somehow if we develop a material at the grain boundary, and so that these particles are stable at high temperature, then the process of grain boundary migration is hampered. This is actually the grain boundary pinning. Now, the ones which are stable at high temperature are basically ceramic materials. So we have somehow you could inculcate a ceramic material in the grain boundary. The grain boundary diffusion can be avoided. So now there are now since again we know that since the grain boundary in the grain boundary region for the driving force required for the grain boundary grow, it also is depending upon the several secondary phases which might have developed at the grain boundary. Now, the secondary phases, like in this case, this additional high temperature stable phase, if they are present in the grain boundary, and an additional energy is required for the grain boundary migration. And since an additional energy is required, so this leads to inhibition of grain boundary motion. Inhibition of grain boundary motion. Now, this secondary phase, the inhibition will not only depend upon the volume fraction, but also the size. So one is the volume fraction, how many or how much area they are covering, and also how large these secondary phase is. Now, this formation of secondary phase can be achieved by several routes. One of them, several powder metallurgical routes. And like high energy ball milling. Okay. Now, the question is actually while creating while creating the secondary phase, we need to take care of another aspect, which is the solubility of the material. Solubility is usually used in the case of a solvent, like a liquid state solvent, where you have a solute and solvent, but it is also used in the case of alloys, where the base material is the solvent and the ones which are being added are the solute. For example, in case of stainless steel, iron is the solvent, and in which carbon is being added as the solute. So it can be an any alloy system. So let's take an alloy system where we have two different types of elements, one A and B. So if we consider the A as the solute and B as the solvent, then the solubility of A in the solvent B is what we need to look for in the case of solubility while studying solubility. And this solubility again is depending upon a thermodynamic quantity called chemical potential. Chemical potential represented as mu, where mu is nothing but is equal to del G by del N at constant V and P, VPT. So N is the number of species, and in this case it is the number of atoms. And in the case where there is a solute A getting dissolved in the solvent P, the mu A will depend upon the number of A atoms available, and we'll call it as mu A. Now, in the case of nanomaterial, it has been found that the solubility is either decreasing in some cases and it is increasing in some cases. And same is the case with this mu A. It's not any particular increase or decrease pattern. Like if you talk about solubility of hydrogen in nanocrystalline palladium, okay, at a concentration of 10 to the power minus 3, less than this concentration. So in this case, since this is a nano, so there is an enhancement of solubility, and let's say temperature is say from 10 Kelvin to so there is an enhancement of solubility 10 to 100 times compared to the coarser palladium crystal. Similarly, magnesium and magnesium-based alloys, which are also used for hydrogen storage applications, the weight percent of hydrogen, if plotted with respect to time, we can see that with the decrease in particle size, there is a mixed trend. So this is how the plot will look like. So there's an increase and there is a decrease. However, with increase in particle size, however, the solubility of the hydrogen increases. Taking another example, the solubility of bismuth in nanocrystalline copper at less than 10 to the power minus 4 concentration at 100 degree centigrade. There's an increase in solubility of 10,000 times. However, there's of course threshold grain size, which is equal to 20 nanometers, for this increase to be observed. If the grain size is more than 10 to the power 1 nanometers, then this effect is no longer existing. So this is very important. This is the threshold grain size. Taking a much technologically vibrant material, for example, if we are considering an alloy of iron and silicon, we find that the solubility uh, of silicon, which is represented by the atomic percentage of silicon in Fe, if we plot this with respect to the grain size, then we get a pattern like this. However, the grain boundary has a different pattern. Along the grain boundary, the pattern is like this. And this is for 25% Si in Fe. So this temperature, this grain size is uh, 20 nanometers. So one can see that there is much less solubility up till this threshold grain has been reduced. So till the size is 20 nanometer, there is almost zero solubility or next to negligible solubility. As soon as the grain size decreases beyond this 20 nanometer size, solubility increases greatly. Now, a similar trend also follows, but not exactly the similar trend, grain boundary. From grain boundary itself, we can see that as the D decreases, automatically the volume fraction of the grain boundary will increase, and this will lead to a higher solubility, atomic percent of the Si at the grain boundary also will keep on increasing. But there is no threshold grain crystallization in the case of grain boundaries, because grain boundaries they are an open structure. Now, due to this solubility, this enhancement of solubility in the case of nanomaterials, many alloys where many alloys have been transformed into a more soluble state. That means if there is an alloy E and B where the solubility limit or the terminal solubility was 30%. That it was not able to go any further beyond that. But taking this material into the nano regime, this has been found to increase it much higher percentage, say 60 or 90%. And most interestingly, there were many alloy systems where the solubility was zero. That is, the alloy could not dissolve into this A. In this case, taking into the nano regime have made them soluble. This is very important aspect of solubility in nanomaterials. Now, how do we make these nanomaterials? That is an interesting question, especially when the solubility factor is there. How do we enhance the diffusion, as I was talking about? We use different ball metallurgical routes. One of the very important routes of synthesized nanomaterial is called high energy ball milling. High energy ball mill, or HEBM, is a process. The principle of this process is there are two rotating discs which are rotating in the opposite direction, and also there are very hard, small hard spheres, and the powder which is need to be processed, which needs to be made nano, is kept inside, is the source material. Now, due to this opposite force, there is a centrifugal force acting, and this centrifugal force makes these nanomaterials, the powders, form powder inserted to nano regime. Okay, so there is a rotating vial, and there is a supporting disc which move in opposite directions. This is the concept of ball milling. Okay, that's it.